Good morning, good afternoon, good evening, greetings. Well, this is really about thermoelectricity, thermopiles, etc. But it's very much a call for help because I've got some. It's one of my favourite topics actually, but I've got some questions that I'd like some help with. I've only really got one earth-shattering epiphany regarding thermoelectricity, which I'll share with you. But first of all, just to remind you, this is a series of videos about alternative energy, sustainable energy, and ultimately we'll talk about types of free energy and types of free energy that might be on the horizon for a brave new world. You'll also see from my earlier videos that I'm recovering from more than severe mental health issues, anxiety and depression. And am I doing this to try and recover and share some information with people, but also to recover my all-terrain four-wheel drive 60-year-old fire engine, which has got a caravan on the top. It's as tall as the London bus, and it's packed full of sustainable energy devices, generative braking, the engine heating the bath water, the log fire heating the engine or heating the fuel, and all sorts of things. Solar power, of course, a massive bank of batteries. But as yet, no thermoelectric generator on the wood stove. We'll go into that. So what is thermoelectricity? Thermoelectricity, of course, is where we turn heat into electricity. It might also sometimes be called a thermopile or just a pile. And it principally is a junction between, or junctions, many junctions between different metals or even different elements. It's a bit more tricky dealing with elements. In this case, it might be something like carbon and clay couples. I should imagine we'll see that, but what we've seen in Victorian times, which actually surpasses what we see in the 20th century actually, is dissimilar metals. So that might be copper and iron typically. So if you imagine, I don't know how to explain it. I think I'm going to have to assume that you know what a thermopile junction looks like, because I don't have the ability to draw something or show you some pictures. I can give you something to look up. If you looked up the Clamond, Clamond thermopile or thermogenerator, you'll see that the Victorians are producing something like 30 amps at 12 volts from their coal-fired room heaters, really, space heaters, and they were taking electricity off them as well. And yet here we are in 2020 and we're not doing anything like as much or as well. So you've got these junctions, and the more of them you have, the higher the voltage. And the voltage is the big problem, really. You need lots of junctions, but each junction has an internal resistance, and it's that internal resistance and the surface area that that affects the current. So we struggle for voltage. The current is there, but because the internal resistance is not always what we want it to be, and because the voltage is so small, we don't see the current that is there with our everyday, especially digital meters. So we all know about thermopiles on gas fires, calogas fires, room fires, portable calogas or butane or propane gas heaters, caravan heaters, etc., gas heaters. They have a thermopile that you have to you have a pilot light, don't you, and that heats up the heats up, and that keeps the gas valve open. Now if you take that all to pieces, you'll find that the gas valve's kept open with a solenoid or a magnetic coil of very thick wire, and so we know straight away that, say the thermopile was giving out 20 millivolts. If that was 20 millivolts at 1 amp, that would be 20 milliwatts, and that would be nothing like enough to hold the gas valve open. And so, almost from common sense point of view, we can see that it's tiring holding this phone. Common sense point of view, we can see that the current must be quite high. Now I've bought a Thompson bridge and other things to try and actually measure the internal resistance and get some facts and figures, and then I've fallen unwell and haven't been able to do any experimentation, I've got to be honest with you, to speak of with thermoelectricity. But I had a friend that did actually measure the current from one of these tiny little piles, and they're I think it was about 16 amps. And of course, if you speak to a contemporary scientist or university boffin, they'll tell you how this is all very useless and that they're not worth bothering with because the voltage is too small. But already there are working thermoelectric nuclear power stations. There's thermoelectric buoys, marine buoys that have radio communications and ongoing light from thermoelectricity. And of course in space they have thermoelectric generators of all different kinds, and in remote areas, Siberia, places like that. I've got some notes here, so I will be looking down and just reminding myself that I don't miss out any sort of important stuff. So we've got the setback coefficient. I don't even remember what it is because I've got no time for it at all. There's just too many anomalies. But the big problem with it is that it doesn't tell us that actually the current is proportional to the surface area of the junction. So if we had massive junctions and lots of them, we'd have a respectable voltage and a respectable current, and therefore respectable power. And so we're going to see Formula 1 cars with thermoelectric units on them. We've already got lorries with them. There'll be one on cars that gives us a few kilowatts. But of course the problem is in the 20th century we want everything small, and the Victorians knew that when it comes to things like soot, which is a nanoparticle, or gases and such like this, a lot of material science, the smaller it is, or the higher the frequency is, another way of looking at that, the more power is available. But when it comes to some of this achievable technology right here, right now, they quite often use like a mile of wire on a massive great iron former, and so it was with these Victorian thermoelectric devices working off fires. They were quite big, but then what's the problem? A fire in a house is quite big, a chimney is quite big, so thermoelectric devices can and could and should be built in these things. The big problem is getting the two dissimilar metals to join together with a low voltage, a low internal resistance. This is the key, plus the number of junctions, plus the surface area. This is just simply not known or talked about almost anywhere. I've spent 10 or 15 years looking for clarification on this, and it's just not there. Now, nuclear thermoelectric power stations very interesting. They have lots of little thermocouples or thermopiles about the size of a 2-penny piece in the UK, or a bit bigger than a dime in the US. Let's say a couple of centimetres across, I think, and then they have loads of them. And here's a question for you. What do you think the temperatures are in a nuclear reactor, and what temperatures do you think there are if it goes critical and melts down? A lot of people would say 1,000,000 degrees, or the heat of the sun. But in fact, these nuclear power station, the temperature is only about 200 degrees C. That's what it needs to be to turn water into steam. If the thing goes critical and melts through the floor, you're still only talking about 1 or 2,000 degrees C, pardon me. So there we have it. Now with the thermoelectric junction, another reason the Seebeck coefficient or formula falls down is that as we increase the temperature with some dissimilar metals, and they like things like bismuth and telerium and all those kinds of things, they don't all behave the same, and sometimes the voltage at a certain temperature reverses. So check that out. You've got a voltmeter on it, it's going up to maybe 2 millivolts as the temperature increases, and then suddenly it dives down and it's minus 2 millivolts. This takes a lot of explaining, and I can't explain it. Well, I haven't tried to be honest. Maybe you can. I mean, it's one of those anomalies that show us that there's a lot more to be learned about thermoelectricity, and just how little we've learned compared to the Victorians of these thermoelectric generators, these little ceramic square white things that you get, or Peltier effect ones for turning electricity into cold, just the reverse effect. They're kind of good, but they're really limited on the temperature range, really limited on the junction size, because they've tried to make them 12 volts, say, or 6 volts, which means an enormous amount of junctions, which means the junctions are going to have to be small, and therefore the current's going to be very limited. So I think they're fun, but I don't think they show us the way forward at all. And I think I said they work on a narrow temperature range, and I think they're quite easy to ruin them. So my advice, anybody interested, is to go straight back to sort of roughly Victorian times and look at how they did it and what they did and what the problems were. And as I said, the problems were not cooling the cold. Oh, the $1 million thing I haven't stated, which I should have stated at the start, was that these junctions between dissimilar metals, one half of the junctions has to be kept cold, so it's in water or cold air or exposed to the environment, and the other side is hot, so it's exposed to the flame, or a gas flame, or a coal-fired burner or a wood-fired burner, and it's this difference in temperature that causes a voltage and a current to be generated. So sorry, I do apologise for forgetting that basic fact. Some of you that aren't technical would be wondering what the hell I've been gabbling on about, so huge apologies for that. So I think Formula 1 cars will have thermoelectric recovery before long. Formula 1 cars about 1,000 horsepower, that's 756 kilowatts, and my prediction is that we might be able to recover, let's say, with a chain of thermoelectric devices on the exhaust, might get maybe 1% of that energy back, which would be 7.5 kilowatts, maybe 3%, which would be 22.5 kilowatts or 30 horsepower. But that's electricity, so 30 horsepower applied to the drivetrain, the electric motor, would be instant. The electric motor gives maximum torque almost instantly, so that would be a very significant contribution, even though it is only 3% in my view. Just trying to look at my note here. Yeah, well, a Formula 1 engine these days is 70 to 80% efficient, so the wasted heat through all the friction losses is only 20%, but that 20% is still something like 160 kilowatts or 200 horsepower. Just turning over the page here a second, 200 horsepower, so it's quite a significant amount of energy that's lost in heat, and of course in road cars. It's much more, because obviously they're not like Formula 1 engines. One of the things that really interests me is the use of minerals. I said elements earlier on, I meant minerals, to make junctions out of, say, clay and carbon. Goodness knows how you get over the internal resistance problem, but they would certainly withstand very high temperatures. The voltage does appear to go up with temperature. And the other thing is, there's a lot of talk about today is carbon nanotubes. Well, I've got another name for carbon nanotubes. It's called soot. And I think we're going to see soot in batteries under another name, possibly with thermoelectric devices. I'm not entirely sure, but the massive surface area of it might mean that we could get low internal resistance. I'm not sure about that. That's where I need your help, really. I'll explain in a minute more deeply how I need your help. Another suggestion was to friction weld the junctions. Another answer would be to silver solder them. I don't know what the effect of including a third metal is going to be. Another option would be to amalgam them with mercury, and I have got the mercury to do that. And so that's really where I want the help. If anybody's interested in experimenting seriously with thermoelectricity, I would certainly want to lend a helping hand in any way that I can. I think that and methane is a huge part of the future. And in previous videos where I've talked about how you can run a car on wood and potatoes and rubber gloves by turning it into a gas, I've also talked about how that's a gasifier, and I've also talked about digesters, how we can digest or anaerobically digest tomatoes, potatoes, cabbages, dandelions, hair, into methane, a very clean burning, sustainable energy. So the gasification is fascinating, but the production of methane through organic produce, waste organic produce, or especially grown organic produce, is the way forwards, in combination with thermoelectricity. Yeah, I'll take a bet on that, prepared to be proved wrong. So the help I need is, how can we get a lot of junctions, and what metals do we choose, materials, and how do we get a low internal resistance joint. I think the small voltage we could handle, because just a few volts at several hundred amps, maybe an electronic boffin can tell me if that would be enough to drive some kind of Igbit or Triac or Thyristor. That's not my bag, electronics, but could it be applied to some inverter that would, a voltage doubler really, I suppose is what we're saying here, so that we can get the voltage up and sacrifice a bit of current to get it to a useful range, which normally starts at about 12 volts, doesn't it? Possibly 6 volts. All depends, I guess, on what we're powering from these devices. I'd like to think that in the same way that we've seen electrostatic machines, maybe we would see low voltage, high current devices, whether that would be a unipolar or a homopolar motor. I don't know, that's a thought. That might work on a small voltage. Oh, so we're opening up a can of worms here, aren't we, on a massive scale. Well, a massive scale in terms of like questions for the head and the brain, and possibilities for the future. I'm probably going to leave this one here. You've had to look at my ugly face all the time. I really apologise for that. I'm really not well. I'm in a coffee shop. I'm hanging on to life by the tiniest of threads, I promise you. And what I want to do really before I leave this planet is to get some ideas across to to you guys. We've not even started yet. My mind goes into and past science fiction, really. I think that some of our science fiction is actually possible, and I've got lots of ideas on why that would be possible. I've done lots of experiments where I've seen inexplicable things, and there's been many good scientists on whose shoulders we stand that have done some astonishing experiments, and I just can't wait to get onto some videos to describe some of those anomalies. And although I don't have all the answers, I promise you faithfully that there's a number of questions we can ask any physics professor, and on asking them his head will implode, because, as I've said in previous videos, modern science, in particular in my view modern physics, is in complete and utter breakdown and disarray. And that's official. It's official because we have official physics and we have official quantum physics, and they just don't marry, and neither does celestial physics doesn't marry. And then you add metaphysics to it, and we're in trouble. So this is the birth of a new age where new technology, new physics will be available to the common man to microgenerate his energy needs on a household or street level, independence from huge corporations and from governments. I think this is what we need to see. But really the world's not really ready for it right now, because there's a lot of greed, and that might be why we haven't seen this technology. The technological revolution, in my view, has not even started. It nearly started about 100 years ago. People like Guthrie Waite and Lord Thompson, and of course Nikola Tesla, Henry Moray, Bruce De Palma. My God, were they on the verge of something absolutely tremendous. But what happened in physics was there was a kind of disagreement really between the relativists, the reductionists, the capitalists, and what would be called the etherists. So that's ether, E-T-H-E-R, or I prefer the spelling A-E-T-H-E-R. And this is a field which, of course, is the question to ask. Well, we won't get into that. We really won't get into that right now, because that will make too many heads blow up. But one leads to high price energy, one leads to freedom, and this is the absolute crux of the matter, that everywhere is an infinitely unmanifested potential, let's put it that way. And much of what we consider to be real is a virtual or dream state, demonstrated no better than the physics attempts at finding the smallest possible quantum with synchrocyclotrons and all sorts of hadron colliders and stuff in Geneva in Switzerland, and they can't find anything. So there's a little teaser for the future, or maybe I've just lost some viewers there. But that's cool. If you'd like to subscribe, I'll be saying much more and asking you for much more help. If you want to make a comment, that's cool. But I think subscribing is the key to getting a few of us together and having a beer or a cup of fresh coffee and just enjoying ourselves, really. One person would have the time, somebody else would have the money, and maybe we can build some really interesting and exciting things. Do please take a look at my truck. If you're of a bohemian or slightly alternative view, you'll find that absolutely fascinating. People generally do. It's one of the most infamous vehicles on the road at the moment. It's my experience of driving it around. Not everyone gets it, of course. Only a small percentage get it, but when they get it, they're super enthusiastic. So, I'm past any of my rather crappy videos. Do pass them on to anybody you think might be interested. I'm not trying to be famous, I just want to get to a critical mass so that we can actually meet each other and get some stuff done, or maybe just talk about it. It doesn't matter. We all know how exciting it is to talk to another person about ideas and inventions that we've got or that people in the past have had. So no mess, I think they say, do they? Peace. Here's a proper picture of what I should look like. Very, very embarrassed by my current state of affairs, so thanks for being patient with me. Laters.